In this video, we are to identify the major type of intermolecular force for the following molecules. So let's go ahead and do iodine first. When we're trying to identify the major intermolecular force, we first start off by drawing the Lewis structure. In this case, the Lewis structure will be the same as the Vesper structure because it's going to be a linear molecule. You can see from the Lewis structure that it's an equal and opposite pole of electronegativity. Therefore, this is a non-polar molecule. And we know that non-polar molecules have dispersion forces as the major intermolecular force. Let's go ahead and do phosphorus trichloride. And I give you the geometry here. It's a trigonal pyramidal molecular geometry. So in its shape, it's going to have a lone pair on the central atom, with one bond going towards the back and one bond going towards yourself, and you have another bond that's in the same plane. Okay, because of the lone pairs that are on the central atom, this shrinks the bond angle that we have to less than 109.5. Chlorine is the most electronegative element, and so our dipole moment is going towards the chlorines. Hence, this is a polar molecule. Since there's no hydrogen bonded to oxygen, or hydrogen bonded to fluorine, or hydrogen bonded to nitrogen, there is no hydrogen bonding. So the major intermolecular force here has to be dipole-dipole. Dipole-dipole forces occur when you have polar molecules. Let's move on to the next molecule, hydrogen sulfide, and it has a bent structure. So we're going to have one of the hydrogens going towards the back and one going towards the front. And it has two sets of lone pair on the central atom. Okay, the lone pairs on the central atom make this portion of the molecule more electronegative, and my hydrogen's more electropositive. My dipole moment's going towards the sulfur. This will be a polar molecule. Hence, the major intermolecular force here is dipole-dipole. Notice here that there is no hydrogen bonded to a fluorine, nitrogen, or oxygen. So there's no hydrogen bonding involved here. A hydrogen is bonded to a sulfur, so it's dipole-dipole. Let's go ahead and move on to carbon monoxide. Which is linear. Again, like in this molecule, dipole moment's going towards oxygen because it's more electronegative than carbon. This is a polar molecule, so this is going to have dipole-dipole forces. Okay, let's look at carbon dioxide. Carbon dioxide has the following structure. Here we have an equal and opposite pole of electronegativity going towards the oxygen. Since there's an equal and opposite pole in carbon dioxide, this is a nonpolar molecule. And remember, all nonpolar molecules have dispersion forces. And our last molecule for this video is our tetrahedral carbon tetrachloride. So let's go ahead and draw our molecule. So we know here that since all the atoms in our tetrahedral molecule are the same, this is going to be nonpolar. Therefore, this is going to have dispersion forces.